Okay, so we're going to continue on with section 2.1, where we finally built the concept of what a derivative is. So I'm starting here on this page that we already finished in the last video, just to reiterate this derivative concept that we built the last part of this lesson. So I'm just reiterating this formula here that we're going to be relying on as we use this limit process to find the derivative of any function. We're going to do a couple different types of functions than we did last time. But before we jump into those, I did want to just stop and remind you guys that this limit process for finding the derivative really was built from that idea of taking the formula for slope of a secant line, so our 2 points, that was taking the two y values of x and x plus delta x, the two y values for those two x values, so that's the difference between the y's, the difference between the x's ended up simplifying to delta x. So we had this equation for the formula, we had the formula for this slope of a secant line, and then as that delta x, as x, the change in x approached 0, what this actually turned into was the slope of the tangent line, which is what a derivative is. Okay, so just wanted to remind you guys, we're going to turn over here and do a couple more. Okay, so for part 2 of this first section of chapter 2, we're going to pick up where we left off, and the purpose of part 1 was to introduce you of the concept of what a derivative is, which, remember, is the slope of the tangent line to a curve at a specific point. And we denote derivative with f prime of x, and we saw that we can calculate the derivative or the formula for the derivative with this limit process. So we're looking for the limit as delta x approaches 0 of f of x plus delta x minus f of x itself, all divided by delta x. So I'm writing that up here on the page. I would encourage you to as well, because we're going to refer to this as we find the derivative of a couple of other functions where the function is a different type. So in the first video, we looked at using this limit process to find the derivative of a linear function as well as quadratic. And now we're going to look at a couple of different types, so rational and square root, because we kind of approach each one a little bit differently. Also, my intention was for you to attempt problems 1 through 3 on the 2.1 homework sheet before moving on in the notes, because going through the process with numbers 1 through 3 on your homework kind of solidifies the limit process in general, which helps trying these next 2 examples go a little more smoothly once you've gone through the process on your own. So if you haven't done that, I would really encourage you to stop and go through 1 through 3 on your homework first, because I think it'll make these problems make a little more sense to you after having a little bit of practice. All right, so number 3, we've got f of x equals 1 over x plus 3. I want to find the derivative of that, which is going to tell me the slope of the tangent line, or the slope at any point on that function. And that is called the derivative. The derivative f prime of x. So we're going to determine that by taking the limit as delta x approaches 0 of f of x plus delta x. So just a little recap here. This is f of x, 1 over x plus 3. So f of x plus delta x, I'm going to replace that x plus 3 with x plus delta x plus 3. So that would be 1 over x plus delta x plus 3. So that's this portion, f of x plus delta x. I've substituted x plus delta x into the function. Now I'm going to subtract the original function f of x. So minus 1 over x plus 3, all divided by delta x. So now we have this very complex fraction here. So we need to work on simplifying that. Before I move forward with this one, I am going to do a little example over here that you could jot down and even erase later, but to simplify these complex fractions, let me give you a basic example. Like if I had something like this, 1 over x divided by 2. think about when I'm multiplying something, or when I'm dividing something by 2, specifically 1 over x. Think about what that is. I'm actually taking 1 over x, and think about, instead of dividing by 2, I could think of it as multiply by 1/2. So this is actually just 1 over 2x. So that goes to dividing fractions. When you divide a fraction, you can actually take the first fraction and multiply by the reciprocal of the second. That's how we're going to treat these. So the first thing I'm going to do is split this fraction divided by delta x minus this fraction divided by delta x. And then from there, we'll be able to simplify even more. So I'm going to take this in very small steps, one at a time. So the first thing I'm going to do is break this down into 2 separate fractions. So we've got the limit as delta x approaches 0. So again, first I'm taking this whole thing divided by delta x. So 1 over x plus delta x plus 3 all over delta x minus 1 over x plus 3 all over delta x. Now I'm going to apply this idea here. Instead of dividing by 2, I multiplied by 1/2. Instead of dividing by delta x, I'm going to multiply by 1 over delta x. What that's going to result in is an entire fraction, a single fraction. So again, instead of dividing by delta x, that's the same as times, let me write it up here so you can see here, that's the same as times 1 over delta x. So instead of doing this, I can just multiply it by 1 over delta x. Same with this, instead of divide by delta x, it's times 1 over delta x. So now I've got this. My first fraction is now 1 over delta x times this whole thing. So parentheses around that, x plus delta x plus 3, and then minus 1 over delta x times x plus 3. So that's coming from right here. All right, so now I've got this whole thing. There's a lot going on here, and we still can't evaluate this by plugging in 0 for delta x, because we would end up with 1 over 0 both times. So we're going to continue manipulating this until we are able to use direct substitution. The best strategy for moving forward with this is, can we simplify this into one single fraction? And that answer would be yes. We would just need a common denominator. So let's think about common denominator between this and this. The good news is they both have delta x. That's great. This one has x plus delta x plus 3. This one just has x plus 3. So I need to take the entire first fraction and multiply it now by x plus 3 over x plus 3 in order to get that x plus 3 down here. So I'm going to take this and multiply by x plus 3 over x plus 3. And now you'll see what my common denominator is going to be. So to get this one to have that common denominator, I need to multiply it by this whole thing, x plus delta x plus 3 in parentheses. So that's going to be times x plus delta x plus 3. But I have to multiply the numerator as well. So what does this result in? Let's see. All right, so now we've got the limit as delta x approaches 0 of a single fraction with its denominator being this whole thing now, delta x times x plus delta x plus 3 times x plus 3. That's my denominator. My numerator from my first fraction up here is just x plus 3 times 1. So x plus 3. And then over here, careful to recognize I'm subtracting. This whole problem has always been subtraction. Subtraction, subtraction. So I'm subtracting this whole thing. And in order to simplify this in one step, I'm just going to go ahead and distribute this negative right now. So that's going to be minus x minus delta x minus 3. So minus x minus delta x minus 3. So this is what we're taking the limit of. Right now, at first glance, we are still unable to use direct substitution. However, if we simplify this numerator, things will clean up pretty nicely. So hopefully you can see I've got x here plus 3 minus x minus delta x minus 3. So this x minus x cancel, and then the 3 minus 3 are also gone. So that positive x, positive 3, negative 3. What's remaining, don't forget to take the sign out front with it, is a negative delta x. So let me rewrite what we've got here. So the limit as delta x approaches 0, all I have left in the numerator is negative delta x. In the denominator, I've got delta x times x plus delta x plus 3 times x plus 3. That's convenient because finally I've simplified. I started out with this very complex fractions within a fraction, rewrote it as all one single fraction, and in doing so, this is what this entire thing simplified to. This whole complicated mess simplified down to this. So this whole thing took us down to this simplified fraction, which is nice because now I have delta x in the numerator, delta x in the denominator. So now I've got negative 1 in the numerator, and now I'm in a position to use direct substitution to plug 0 in for the only remaining delta x right here. So when we do that, we're left with a limit of negative 1 in the numerator. So I'm going to just simplify this. F prime of x, the derivative of f of x is negative 1 divided by, now think about what happens when I plug 0 in for delta x. That's just x plus 3 times x plus 3. So that results in a final denominator of x plus 3 squared. This is my derivative. Now the reason I wanted you to do 1, 2, and 3 on the homework before you got here is because it's really easy to get lost in the algebra and all of these simplification steps and miss sight of this derivative from the limit process. Once you lock in what we're doing with this limit process, then you can kind of focus on the messy algebra to get to here. So here we have the derivative of f of x for number 3. Before we move on, I want to give you guys a visual of what the heck just happened. So we have this function f of x, which is 1 over x plus 3. Let's take a look at what our function looks like. All right, so here is a graph of 1 over x plus 3 right here. I know I'm covering up all of our work, but now that we've gotten to our derivative, I want to relate it to that. So f of x plus 3, f of x equals 1 over x plus 3. We're looking at this graph right here. So this graph should look familiar. It's the function 1 over x, but the plus 3 means we've shifted 3 left, and now we've got this horizontal asymptote at negative 3. And here we have the derivative, which is telling us slope of the tangent line, which means if I want to know the slope at any point on this graph, it's going to change. It changes point to point, right? But let's say I want to know the slope right here at negative 2. The slope right here at negative 2, how is this function changing at negative 2? Well, if I can figure out the slope of the tangent line at negative 2, which is going to look something like that, then I know exactly how this function is changing at negative 2. So now that I have this formula, f prime of x, this is the formula I'm using. This is going to determine slope right there at negative 2. All I have to do is plug in negative 2 right here. So when we do that, we would have, I'm just going to do it right here on the graph, f prime of negative 2 means, let's see, that's negative 1 in the numerator. I plug negative 2 in here, add 3, and I get positive 1. Square 1 and you get 1. So right here we get f of negative 2 equals negative 1. What does that mean? It means the slope of this tangent line right there at -2 is -1. That makes sense. Visually, we can see how a slope of -1 makes sense. And we know that at that instant, at -2 on our curve right here, the function is changing at a rate of -1. So we could also figure out the slope at -1. All we would have to do is plug in -1 to our formula. So let's see what that would be. If I want to find the derivative at -1, we would just evaluate f prime of -1. That would be -1 in the numerator. Take -1 and plug it in here. Add 3 to -1 and you get +2. Square it and you get 4. So -1/4. That's what we are told the slope is right here. Let me get another color. Let's get green right here. -1. Think about a tangent line right there. How it would kind of be a lot flatter. That makes sense. A slope of -4, down 1/4, down 1/4. That's how that function is changing right here. But we used this same formula. That's what's so great about this formula for a derivative. We can plug in any x value and figure out what the slope is right there. So that's kind of a quick visual of what all of this is doing for us to help us understand this function better and how its rate of change is changing. Okay, I really hope all this is making sense. I know it's a lot to digest all at once. Let's go ahead and move on to another example here. So let's look at example 4. We've got another type of problem that we're looking at. We're looking at a square root function now. So let's see, I gotta get rid of this thing. Get rid of, yep. Uh-oh, okay. All right, so now I am looking at f of x is x, square root of x plus 2. I want to find the derivative of that, slope of that. So let's see, f prime of x. We're going to find that by evaluating the limit as delta x approaches 0 of f of x plus delta x. So remember, that means I'm just taking my function and replacing x with x plus delta x. So that would be the square root of x plus delta x plus 2 minus f of x, the original function, square root of x plus 2, divided by delta x. So here's my original, just applying my formula for a derivative. This is the limit I need to evaluate. Plugging in delta x, replacing that with 0. If I replace this with 0, I would end up with the square root of x plus 2 minus the square root of x plus 2 divided by delta x. That would be 0 over 0. So we need to do something here to change this. What are we going to do? Well, if you think back to chapter 1, we had entire problems where we were just finding limits like this, and we had a strategy of rationalizing the numerator. And in that process, this whole thing simplified pretty nicely. So that's what we need to do, is rationalize the numerator. Let me get some more space over here. Okay, so rationalizing this numerator means I'm going to multiply the top and the bottom by the reverse of this whole numerator, except changing that minus to a plus. So I'm multiplying this whole thing by the square root of x plus delta x plus 2 plus the square root of x plus 2. And remember, these always start out like really intense looking, but they do simplify nicely. So then I'm multiplying by that same thing in the denominator, because we don't want to change the value of this problem. So we're really just essentially multiplying by 1. Okay, now when we do this, remember, we do it intentionally because when we when we distribute these through, it cancels out. Things simplify really nicely. So I'm going to take this first one and multiply by that first one. What's going to happen when I take this square root of x plus delta x plus 2 and multiply it by itself, essentially squaring it? The square root is then gone. So we are left with, the limit as delta x approaches 0 of just x plus delta x plus 2. Then I multiply it by this fraction, so the positive root x plus 2. Then I take the negative root x plus 2 and multiply it by the square root of x plus delta x plus 2. These two, so from here to here, that product minus this product, they cancel each other out. That's why we do this whole thing. Then my last product will be this negative root x plus 2 times positive root x plus 2, which is this, the negative x plus 2. So we've been doing problems like this for a little while now. Hopefully that all made sense. My denominator, don't bother distributing anything. Just write delta x times this whole thing. So delta x times the square root of x plus delta x plus 2 plus the square root of x plus 1. All right, so what's going to happen here is up in the numerator we've got x plus delta x plus 2 minus, so this needs distributed, so it's really minus x minus 2. So let me rewrite that. This is actually minus x minus 2 once you distribute that negative. So now we've got positive x and a negative x, a positive 2, and a negative 2. So that cancels out very nicely. X's are gone, 2's are gone. All we're left with is the limit as delta x approaches 0 of delta x divided by delta x times the square root of x plus delta x plus 2. I just realized times the square root of x plus 2. I magically changed this into a 1. That should never have happened. Some of you hopefully are paying close enough attention that you recognized that mistake. Okay, so that should be a 2 the whole time. Okay, the great thing about this is that now we have delta x over delta x. We can cancel that out and we're left with 1 over this whole thing. Now we're in a position where we can take 0 and directly substitute it in. So that would give us with this final solution for the derivative f prime of x. When I plug 0 in here, it's just the square root of x plus 0 plus 2. That's just the square root of x plus 2. Let me write it out. I don't want to skip too many problems here, too many steps. 1 over the square root of x plus 2. That's what this is going to turn into. Plus the square root of x plus 2, right here. So that simplifies to 1 over 2 times the square root of x plus 2. I have one of them here, one of them here, so I have 2 of them. So this is the derivative f prime of x when f of x is the square root of x plus 2. All right, what does this derivative tell us? It will tell us the slope of this function at any given x value. So let's look at a quick visual of our function just so we can piece this together. Okay, so now we're looking at our function. This shape should make sense. It's a square root function and it's been shifted left too. So let's think about the rate of change of this function at a specific point. Let's think about it when x equals -1. Let's say I wanted to know right here when x is -1 what the rate of change of this function would be, and it would be the same as whatever the slope of that tangent line right there is. Well, now I have a formula for the slope of that tangent line. All I would have to do is plug in 1 right here, or -1 right here. So that would mean when I plug -1, let me get another. So if I want to know the rate of change right here, I would evaluate f prime of -1. Go down to my f prime formula, that would be 1 over 2 times the square root of -1 plus 2. -1 plus 2 is 1. So the square root of 1, which is 1. So this gives me a slope of 1/2, a derivative of 1/2 right here. That means the rate of change right here is 1/2, which makes sense. Up 1 over 2, up 1 over 2. But that's only for this exact x value, -1. Think about what the slope would be a little farther out. This curve starts growing pretty quickly, but then it slowly evens out. So I could find the slope at any point here. It's not quite linear, so that slope is steadily changing as x changes. But I could find that rate of change for any x value by using this formula now. Okay, we're going to move forward with one new type of problem. It's the same idea here, but we're going to extend this a little bit farther. So let's move on. Okay, I love this problem because any problem with a graph and a visual, just for me at least, helps solidify what's going on here. So in number 5, we're told to find the derivative at this specific point. So we're going to find the derivative at when x is -2. So this point is on this. We're going to find the equation of the tangent, or the slope of the tangent line there, and then it asks us to find the actual equation of that tangent line. And so this should all make sense when we look at the graph. This is a graph we can easily put together, and we understand linear graphs, so a tangent line is a line, and we understand those types of functions well too. So let's put this all together. So we've got our function is x squared minus 2. The function x squared we know as the parent function of a parabola, and that minus 2 just means we're shifting down 2 on the y-axis. So this is our vertex right here, and then from there we know the shape of this graph goes over 1, up 1, and then if I go out 2, then that squared would be 4. So I'm going to go over 2 and then add 4 to that. So I'm over at this point right here. Likewise, when I go -2 or left 2, I'm going to square that and go up 4 there. So hopefully this quick sketch is making sense for you guys. Okay, I could go over 3 as well, and then I would move up 9, duh. So I could go 3 out, and then I would go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 right there. And same with 3 out on this side as well. Okay, so I've got the points for my graph. Let's try and get a nice clean parabola right here. So I'm going to go, okay, that might be as good as it gets for me. Okay, so the derivative, I want to know the derivative at this point. So there is a shortcut way to this, but for the sake of time and the fact that we're doing all of this unit remotely, we are going to stick with what we know. So don't worry, lots of shortcuts are coming next on the next video. But for this one, we're using the limit process. So we need the limit as delta x approaches 0 of f of x plus delta x. So that's going to be, instead of x squared minus 2, it's x plus delta x squared minus 2 minus delta x itself, which is minus x squared minus 2, all over delta x. So we have some simplifying to do. I'm going to actually expand this and distribute this negative, and we'll see some convenient cancellations take place. So let me try and write a little smaller here. The limit as delta x approaches 0. All right, as I expand this, if you need an area model for that, go for it. So it's going to be, let me see if I can find, I'll do it over here to the right. X plus delta x times x plus delta x. If you need the area model, do it. That's going to be x delta x. Okay, so that's going to be x squared, x times delta x, another x times delta x, and delta x squared. Okay, so that whole thing is, whoops, that's x squared. So x squared plus 2x times delta x. I'm going through this pretty quickly because we did lots of this in the first notes video. And then plus delta x squared. Okay, all I've done is expand this to this. So I still have all of this to tack onto it. So the minus 2, and then minus x squared plus 2. And that's all over delta x. Okay, so what did that do for us? I've got positive x squared here, negative x squared here, and negative 2 and positive 2. So let me reflect all of that. So this x squared cancels with negative x squared, negative 2, and positive 2. So we're left with two terms up here. This is 2x times delta x plus delta x squared all over delta x. The convenient thing, what's helpful about this numerator is both terms have delta x. So I'm going to rewrite it with factoring that delta x out. Delta x approaches 0. Alright, so I'm going to factor this delta x out of the numerator, and I'm left with 2x plus a single delta x all over delta x. Alright, it's not pretty, but the process simplifies it so that we can cancel out those delta x's now. So let's recap. We've got our limit, or our derivative, f prime of x, starting here, simplifies all the way to this limit as delta x approaches 0, where now we can use direct substitution and plug 0 in for delta x, and we're left with our derivative of simply 2x. This is the equation for the tangent line to this curve, our parabola, for any value of x. To calculate the slope, all we would do is double it. How does that make sense? There's so many things we could talk about here with this, but let's answer our problem. We were told to find the derivative at negative 2, 2. Let's look at negative 2, 2. That's a point on our curve. What is the slope of the tangent line right there? Well, here we have the formula. If I want to know for this x value, it's the x value that we're really paying attention to, f prime of negative 2, I'm plugging that into the formula that we just worked so hard to derive. We plug negative 2 in. So that would be 2 times negative 2, which is negative 4. So what we have is a tangent line right here, and its slope is negative 4. That should make sense just based on visually what's happening right there on the graph. And then it asks for, right here, we are asked to find the actual equation of the tangent line. We have the slope of the tangent line, but the equation of the tangent line, we know equations of lines are y equals mx plus b. Well, we know the slope of that line, which is the derivative at negative 2. So what we're finding is the actual equation of this line. So we could just plug in what we know, negative 4x plus b. Now I need to know what b is. Well, considering we're finding this for the point negative 2, 2, we have that point on our line as well. Negative 2, 2 is on this line. So I can plug my y value of 2 in, plug my x value of negative 2 in, and solve for b. So that would be 2 equals positive 8 plus b. Subtract 8 from both sides, and we get b equals negative 6. So that will give us with our tangent line. So here we found the derivative at negative 2, and the equation of the tangent line is y equals negative 4x minus 6. Just to reiterate, the derivative is the slope of the tangent line at that point. Then we just finished finding the equation of that tangent line here, which should make sense. If I've got a y-intercept of -6, a slope of -4, that would give me these points here, here, here. So here's the equation of that tangent line. Hopefully this is all coming together. I like these problems with the visuals. There's a couple on your homework like this just because I think it helps us wrap our minds around a whole lot of things going on at the same time. Okay, so the rest of these notes will go by pretty quickly. Let's flip on over, and we just have a few cases to look at where you cannot find the derivative of a function, and then we'll be done. So flip on, working for you guys, and we'll talk soon. Okay, here we have this alternative form of a derivative. I am not going to spend time going over this. Again, I'm trying to keep this as simple as possible. This is not, if you're interested in it, you can certainly follow along or find other videos on it. It's not a far stretch from what we've already done, but I don't want to overcomplicate it if we don't need to. Let's just talk about when a function is not differentiable. Remember, the word differentiable means, are you able to find the derivative? Or in other words, if we really think about it, are you able to find the slope of the tangent line to the function right there? So can we find the slope of the tangent line at a point? Sometimes you can't. If the function is not continuous at a point, then you can't find the derivative. So taking a quick look at this step function here, this is that greatest integer function that we talked briefly about. How can I find the slope where the function is not continuous? So this function jumps from here to here, so finding the slope at 0 or at 1 or at 2 is not possible because the function isn't continuous there. So you can't find the derivative if it's not continuous at a point. So that's the first case, if it's not continuous at a point. The second case is if there's a sharp turn. So on any absolute value function at the vertex, there is a sharp turn there, and you can't find the derivative of that at 2 because of the behavior of the function right there. It's not a curve, it's just a sharp point, and the rate of change isn't defined right there. So you cannot find the derivative at a sharp turn right there. The other time you can't find the derivative is if that tangent line happens to be vertical. So in this is an interesting case, I think. So if I'm talking about the tangent line right here where this function is actually vertical for a split second at 0, you can't find the derivative there because the slope of a tangent line, or the slope of a vertical line, think change in y over change in x, there is no change in x. So this slope is undefined, which means the derivative is undefined because derivative is slope of the tangent line. So this is just a quick glimpse at where and why you can't find the derivative. If it's discontinuous at that specific point, if there's a sharp turn at a specific point. So I can find the derivative at other points on this function, just not at 2. Or if there's a vertical tangent line. Again, I can find the derivative at other points on this function, just not at 0. Okay, so that's it. That's it for finding the derivative of a function using the limit process, which is a bulky process, but in the next section, 2.2, you'll find all the fun shortcuts, and I think you'll enjoy that a little bit more. Okay, until then.